the first big thing that we're going to do in physics, first big idea we're going to do in physics, is to describe motion. To describe where things are and how they're changing where they are, and how fast they're changing where they are. It's called kinematics, the study of motion. So the first thing we have to do is, where is something? Like, here's my little toy car of science. What if I wanted to describe where this thing is? Well, I can give like long directions, but what we're going to do is we're going to start off really simple. And instead of giving directions in three-dimensional space in a classroom, blah, 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 we're just going to describe where this thing is along a straight line. So here's a straight line, and maybe here's my little toy car. Well, if I want to describe where this thing is on the line, I have to have a place where we all agree we know where it is. What do we call that location in space where we all agree we know where it is on a straight line like this? Anybody know what we call it? We call it the origin. And how far is the origin from itself? 0. The origin, by definition of the origin, has a position of 0. Let's do. So let's say 1, 2, 3, 4, 5, 6, 7, 8. So we have to increment this. And we'll call this the x-axis. Now, what are these increments? What do they mean? How far, what is the length of each increment here? Well, we're going to use meters. So this is 4 meters from the origin. Okay? So I can say, so the origin is where we measure things from. We all have to, it's a location in space, we all know where it is. But where is the little toy car? From the origin, it's 4 meters away. And since we're calling this the x-axis, I can call this a position. Position is the location with respect to the origin. Now we're calling this the x-axis, so we're going to use the letter x to represent position. And we say, well, where is this car? Well, you're going to say it's at x equals, well, I'll put it up here. X equals 4 meters. Does that make sense? Okay, easy. Well, but, oh, I kind of messed this up. 3, let me put it, I'm going to squeeze it in over here, sorry. 1, 2, 3. But there's another place that's 4 meters from the origin, and that's way over here. Way over. So if I said, hey, the little toy car is 4 meters on the x-axis from the origin, well, that's not good enough, because the car could be on this side of the origin or on the other side of the origin. How do we distinguish between which side of the origin it is? Well, we use, right, negatives. And so over here we say x equals negative 4 meters. So x, so it's at so what does this negative mean? Does this mean that we lost 4 meters? Took 4 meters away? No. It means it's 4 meters from the origin, but to the left. Well, this is positive 4 meters. What does the positive mean? 4 meters to the right. So in order to give position, I need to have a magnitude and a direction. I need to describe how far away it is and in what direction is it that far away. Now, what do we call quantities that have magnitude and direction? You need a spatial direction to describe them. Anybody know? I think some of your math classes you talk about them. Quantities that require a spatial direction as well as a magnitude, they also require direction. They're called vectors. Position is a vector. A vector has a magnitude and a direction. In this case, if I said, x equals 4 meters, the 4 meters is the magnitude. And the positive, which we usually don't write the positive there. If we leave it off, we just assume it's positive. But what is that positive? That's the direction. Okay. So we've defined position, and we've described it as a vector. Oh, we can draw it too. We can say, hey, a position vector, we can draw, anytime we have a vector quantity, we can draw a picture of it as an arrow. So I'm going to start at the origin and go out to here. This is a position vector. And position vectors always start at the origin and go out to where the object is located in space. So here, the object is located over here, right to the left. But here the position is to the right. Now, let's say this car is on the move. As time goes by, maybe it's rolling along. It's got wheels. It's rolling along. So let's say, well, when I first look at it, it's right here. But then I look at it a little bit later, maybe 2 seconds later or whatever, and I notice that it's right here. What is its position now? How far from the origin is my little toy car? All the way out here. Well, x equals positive 7 meters. Now, I'm going to say this is where, let's pretend that we're looking at the car as it moved from here over to here. I'm going to call this the initial position, because that's where it was initially when we were first looking at it. And then I'm going to call this the final position, because after a little bit of time went by, it was located right here. Now let me ask you this. By how much did it change its position? How much did this little car change its position? 3 meters. And how did you get 3 meters? What'd you do? Well, start at 4. Well, one way to do it is just to count, right? 1, 2, 3 meters to the right. So that's a change in position. A change in position. Now, change. In mathematics, you probably remember this. In mathematics, when a quantity is changing, we're looking at how much a quantity changed. What's the symbol for change? Yeah, delta. Little triangle. The Greek letter delta. A change in position. And you would say, oh, in this case, the change in position when you went from 4 meters to 7 meters, we went 1, 2, 3 meters. And it was a positive change. Our change position was to the right. Well, how do we get 3 meters? What's another way of getting to? I mean, you could count 1, 2, 3, but what if you're dealing with really big numbers? What if this was at 427 meters away, and this was 764 meters away? How would you figure out how many meters it changed? What would you do? Subtract. And what you subtract what from what? Yeah. Exactly. So we had 7 meters. We ended up at 7 meters, but we started at 4. So 7 minus 4 is 3 meters. Yes? So really, the way we're going to define change in position, by definition, have you ever seen a little 3 equal sign that looks like that? This means, hey, this isn't equal because it's equal. It's equal because we say it's equal. We're defining a thing here. We're defining delta x as being x final minus x initial. This is by definition. And this delta x, x final minus x initial, we call this a change in position, is also called displacement. Okay. Well, what if I went, what if the car is right here, and let's say it starts at 7 meters and it goes all the way, oh, one thing, before I get to that, hold on. I can draw an arrow, a displacement arrow. Starts here and goes here. Now, how is a displacement arrow different from a position arrow? Well, where does a position arrow always start? At the origin. You're describing where it is compared to the origin. Whereas a displacement vector is saying it started here and it ended here. So we have 3 meters to the right. So displacement vectors are a little bit different than position vectors. They're defined differently. So what's the displacement vector from here to here? Well, we can say, delta x equals x final minus x initial. And so we could say, well, where's x final? Well, it's over here. It's over here. So we'll say x final is negative 4 meters. Where was my initial position? Well, let's say we started over here. So it's going to be minus 7 meters. So what is negative 4 minus 7? Negative 11 meters. Now what is the 11 meters? That's a magnitude. That means we had to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 meters this way. And what does the negative mean? To the left. So the magnitude, direction. So therefore, displacement is a vector quantity. And quite often, if things are a vector quantity, we'll put little arrows over the top of them, like this. To distinguish them from non-vector quantities. Now, non-vector quantities are called scalars. And they are quantities without direction. Quantities without direction. Now, I'll give you an example of a quantity without direction. Time. Let's see, we have about 6 minutes left in class. 6 minutes. Now, that's a span of time, right? We have 6 minutes of time before class is over. I would never say 6 minutes to the north. Okay? Or how much, what time is it? Oh, it's about 1:40 p.m. to the west. It makes no sense to give a spatial direction to time. Time has no spatial direction. It has, you might say if there's a flow of time, like go forward in time or backward in time, but that's not a spatial direction. That's not up, down, right, left, forward, backward. So therefore, time is a scalar. But, and speaking of time, when I went from 4 meters to 7 meters, it took time to do that, didn't it? And if I take the displacement and I divided it by how much time it takes, I get what's called, am I off screen? Yes, I'm off screen. I get what's called average velocity. Average velocity. And I'm going to give you a definition for it. We'll do this. And I'm having to rush through this. Sorry, I only got 4 minutes left. Average velocity by definition. Well, look at how much you changed your position. What was your total displacement? And divide that by how much time it took to go that far. And this is your average, this is defined to be average velocity. It's kind of a measure of the rate at which you're changing your position over a given time interval. So it's different than speed. And we're running out of time right now. We'll talk about the difference between speed and average velocity, speed and instant. Now, let's talk about instantaneous velocity. Instantaneous velocity is the rate at which you're changing your position at a particular instant in time. How fast are you going right now? Not averaged out over like a few minutes or a few seconds, but at that instant in time. When you are driving in your car and you look at your speedometer, it's telling you how fast you're going right that instant, not averaged out over your whole trip, but how fast you're going right then. How much the rate at which you're changing position per unit time for that instant in time. And so I'm going to go like this. Now, later on, we're going to drop the INST for instantaneous. But by definition, it is equal to delta x over delta t. But where delta t is right now, what does that mean if I say delta t is right now? What is true about delta t if you're talking about an instant? Delta t is teensy, the technical term is teensy weensy, right? Delta t is tiny. It's for the smallest possible conceivable span of time. It's infinitesimally small. And we say that by taking the limit and letting delta t approach 0. In other words, delta t can't be equal to 0, right? Because you can't divide by 0. But you can let delta t approach 0, and what you get is you get a velocity that is how fast you're going and in what direction. You have to include direction with it at that instant in time. So when you're driving west on the freeway and you're going 65 miles per hour, you'd say my instantaneous velocity is 65 miles per hour to the west. You have to include the direction. Now, if you average, your average velocity might be a lot different, because here it's what your displacement is averaged out over a span of time. Okay, so this is just barely enough for you to give the homework a try, which is what I want you to do. Okay, that is all.